Here's part 4 of the video key for the practice exam. Sorry, it's a day punctuated with meetings. We're going to look through problems 12 through 15 in this part of the video. Problem 12 has us consider the table of reduction half reaction potentials to design a battery made with tin, nickel, and zinc. The reduction half reaction chart will be given to you. And notice these are all written as reduction half reactions. For a cell to work, you need one that is a reduction reaction that is written the way it is here, and one that is an oxidation reaction that is flipped to be the reverse, right? A reaction that liberates electrons. E cells are spontaneous when they have a positive value. So things at the top of the table are very spontaneous. If you think about it, for example, peroxide dismutates into water very quickly. So these things tend to go in the direction they're written, whereas things on the bottom tend to go in the reverse reaction. For example, sodium metal reacts very strongly with water. So in general, you want to have the biggest, most positive E cell value to make a good battery. So let's consider the metals that are in our problem: tin, nickel, and zinc. Here's tin, here's nickel, and here's zinc. So the one that we want going in the forward direction is the one closest to the top of the table. So that would be tin. And that would go in the direction that it's written. Interestingly, the reaction that's on here is just the conversion of the ions. It doesn't go all the way to the metal, just to a different oxidation state of the ion. So I assume that going all the way to the metal would actually be even bigger. And then when choosing between nickel and zinc, zinc is farther down on the table, has a more negative value. Notice when we flip this reaction, it's a state function. So when you reverse the reaction, you reverse the sign when you do that. So instead of being negative 0.76, it's positive 0.76, and the value from the table for tin was 0.15. So now when you add those together, 0.91. Not as good as a 9-volt battery, but getting there. So that would be the voltage that you could generate. So that's the second part. And a galvanic cell is where we have the two separate parts, where we separate the two half reactions. I'm going to put them in two beakers. We'll have the metal in either case in the solution containing the ion. So for example, the tin half cell would have a piece of tin and a tin 4+ solution. And that's where the wire would come through, and we'd have some kind of voltmeter here. That gives us our readout. We expect a voltage of 0.091. And then in the other one, we'd have a piece of zinc metal with a zinc solution. There's one more piece of things that we need to allow to move. Your book showed it as a semi-permeable membrane. You could also use a piece of string soaked in salt that just goes from the other. So you need some kind of salt bridge. Because notice when we wrote these, we wrote net ionic equation. There has to be some kind of counter ion, a chloride or a nitrate or something that is going between these two half reactions, because you cannot allow charge to build up. If the electrons are moving through the wire, they have to go somewhere. I drew this backwards, but let's think about the direction the electrons are moving. So the electrons are being generated in the oxidation half reaction, and that's the zinc one, so that's the anode. Usually you draw the anode on the left. It doesn't hugely matter, it's just a convention. And that's where oxidation happens. And the electrons travel through the wire to the other half cell, which is called the cathode. Remember, if you need a mnemonic, cathode has a plus, that's where you're adding electrons. The anode is negative, that's where you're generating electrons. So this is where reduction happens. Okay, switching topics. Number 13, we've got an unknown monoprotic acid. Monoprotic acid, mono means one, so it means protic means proton, so it has one proton. So we have some unknown. If it reacts with NaOH, because it only has one, we know the stoichiometry of this reaction. We're going to make Na, whatever the rest of the acid is, plus water. So it's got a 1-to-1 molarity. And we need 36.73 milliliters of NaOH, and it's 0.1000 molarity. Notice that has 4 significant digits because all of those zeros after the decimal are significant. To titrate it, and we used 0.750 grams of the acid. All right, let's think about what we need. We want to calculate the molar mass of the acid. Molar mass has mass over moles. We have the mass, right? So we have 0.750 grams of the acid, and what we need to know are the moles of the acid. So we need a way of finding moles. We have a balanced equation. We have a molarity and a volume for NaOH, which gives us moles of NaOH. And if we know the moles of NaOH, we can find the moles of the acid. So let's work through that. We have 36.73 milliliters of NaOH. Remember, being really careful about marking your units will help you a ton. There are 1,000 milliliters in 1 liter. And we have a molarity of 0.1000 moles of NaOH. And we know from the mole ratio that there's 1 mole of NaOH per 1 mole of HX. All right, let's check our units and make sure we set it up correctly. So we had milliliters on top. That cancels with that. The liters cancels there. The moles NaOH cancel out, and we get moles of HX. Notice this is all moving decimal spots, but we can do it. So 36.73 times 0.1 divided by 1,000. 0.003673. So we're going to plug that number into our equation up above. I did 1 over x, that's where that number came from. We get 204.19 grams per mole. And that is a reasonable mass for a molecular weight. Notice if you got something that's a decimal point, it doesn't make sense. So make sure your answer makes sense. That is a reasonable number for that. All right, let's look at problem 14. It's a gas law problem. Oops, I moved it up too far. So we have a mass of a gas, a volume. We have a volume. Let's make a table of what we know. We have a volume of 846.0 milliliters. We have a pressure of 995.0 torr and a temperature of 36.0 degrees Celsius. All right, let's look at the problem. What are we trying to find? We want the molar mass again. Hey, look, we have 2 ways of finding molar mass. We can find molar mass from titration, and we can also find it from gas laws. Ooh, Important tool. So we have the mass, right? Molar mass is grams per mole. And we have the mass, 350 grams. It's easy to measure the mass, right? You throw something on the scale. What we need to find are the moles having volume, pressure, and temperature. So we recall our gas law as PV equals nRT. And what we're going to solve for is N. Our pressure is currently in torr. So unless you're using another unit of R, which you can look up if you like, I find it easier just to know 1, or 760 torr for 1 atmosphere. Our volume, so there's P. Volume is 846.0 milliliters. And normally we have volume in liters. There are 1,000 milliliters in 1 liter. We're solving for N, which means we need to move RT to the other side. So let's go ahead and do that. Make sure you're careful about your units. And notice moles is on the bottom of the bottom, which means it's going to end up on top when we're done with our math. And notice temperature is in Kelvin, which means we need to have our temperature in Kelvin. To convert to Kelvin, you just add 273.15 to the Celsius temperature. And then we're going to put it in your calculator. So 995 divided by 760. Notice that is higher than 1 atmosphere. It's 1.39 atmospheres. I'm going to multiply that by the next part. So we have 846 divided by 1,000. So on the top, we've got 1.107. And divide all that. Use the parentheses. 0.08206 times, and use another parentheses. If you're nervous about using parentheses, go ahead and write out each individual stage before you put it all together. So at the end of it, I got 0.04366 moles. Let's look at sig figs. We had 4 in the milliliters, 4 in the pressure, 3 in the temperature, but when we did addition, we got an extra one. So having 4 in our answer is reasonable. You might say, is that a reasonable answer? While our pressure was higher than 1 atmosphere, it's not that much higher than 1 atmosphere. The volume was a little bit less than a liter. At standard temperature and pressure, 1 mole is 22.4 liters. So it's definitely smaller than a mole. And our temperature was slightly above STP. So it makes sense that our number of moles is less than 1. And less than 1/20th, approximately. So that gets us our moles. From moles, we need to get to molar mass. Remember, molar mass is grams over moles. Something underneath my paper. So we have 3.50 grams of sample and 0.04366 moles. I use my 1 over x key again. And we got 80.16. Notice we only have 3 on the top, so that's going to round to 80.2 grams per mole. And is that a reasonable mass for a gas? Yeah, it's in the realm of possibilities. There are molecules that were 80 that are gases. So yes, that's a reasonable answer. Okay, let's look at number 15. We're going to make a baking soda volcano with sodium bicarbonate and vinegar. So let's start by balancing the reaction. Notice we actually balanced this reaction earlier on the problem set. So, might be a fun problem to do. So this is an example of a double displacement, right? So we're going to swap the protons. Remember, when we do that swap, we make H2CO3, which dissociates to form water and carbon dioxide. And the other swap we get is the sodium acetate. I worked through that in more gory detail on the earlier problem with that. So that was problem 4. So if you want to have questions about that, go look at problem 4. It also included writing the net ionic equation. Remember that weak acids are weak. They do not completely dissociate in water, so they stay together. Sodium bicarbonate is a solid, so it stays together. Water is a molecule, so it stays together. CO2 is a gas, so it stays together. The only thing that comes apart is the aqueous sodium acetate. Make sure you include states and coefficients on all of your numbers. There's nothing that cancels out, so that's the net ionic equation is the same as the complete ionic equation. And let's see if we can come up with a theoretical yield of CO2. This is a limiting reagent problem because we have the mass of each mass of one reactant and the moles of the other. So we're going to practice doing both kinds of limiting reagent problems. Let's do the vinegar first. Notice it's a 1-to-1 mole ratio for both of them. Okay, so we have 85 milliliters of acetic acid. And there are 1,000 milliliters in 1 liter. And the molarity is 1 liter has 0.825 moles of acetic acid. You might think about, does that compare with what you got for molarity in lab? I think it's pretty close. So that gets us to moles of vinegar. We want to get to moles of gas. We know for every 1 mole of acetic acid, you get 1 mole of CO2. So we can put that in our calculator. I tend to multiply all the things on the top and then divide by the numbers on the bottom. So 0.0701. Let's see here, we started off with 85.0, so we had 3 sig figs, 3 sig figs, 3 sig figs is a reasonable number for our answer. Okay, let's do that same thing for the sodium bicarbonate. First, we need to add up the molar mass of sodium bicarbonate. So we need to look up sodium, carbon, hydrogen, and 3 oxygens from our formula. So I'll break out the handy dandy periodic table. So we have 22.99, 12.011, 1.0079, and 3 times 15.999. After a while, you start having them in your head. So 84.01 is the molar mass of sodium bicarbonate. Okay, so sodium bicarbonate. We again want to get to moles of CO2, so a lot of this back end stuff is going to stay the same. So we know we get 1 mole CO2 for every 1 mole of sodium bicarbonate. So this is a demonstration of working backwards because we want to get moles of CO2 on the top. So let's start there. Now I need something that's going to cancel out that moles of sodium bicarbonate. Since it's a solid, we can use the molar mass to get from moles to grams. You know that 1 mole of sodium bicarbonate weighs 84.01 grams. And we had 5.00 grams of it. Okay, if we did everything right, all the units except for moles CO2 should cancel out. So the moles of bicarbonate cancel, the grams of bicarbonate cancel. Boom, we got it. So let's see what we got. So 0.0595 moles of CO2. So which one is limiting? Turns out the baking soda is limiting. So that's how many moles of CO2 we're going to get. So the sodium bicarbonate is limiting. So how big of a volume is that going to be? Notice we have moles. We want to get volume. So if we look at PV equals nRT and rearrange for volume, V equals nRT over P, right? We just divided both sides by P. We have our answer for moles from the last problem. Are 0.08206 liter atmosphere per mole Kelvin. Our temperature, it says, are 25 degrees Celsius, so we're going to have to convert to Kelvin. So we do 25 plus 273.15. So our temperature is at 298.15 Kelvin. And our pressure is at 1.0 atmosphere. So now we can multiply that through. And we get 1.45. We have 3 sig figs, so 3 sig figs. It's going to round to 1.46 liters, which is enough to blow up a balloon, but not explode your house. So that's how you solve that one. And that is the end. We made it. Good luck.